Okay, I will do another one example. That is 3.25 question in the reference book. Okay. Uh, so in previous physical class, I have done, as I can remember, I have done three questions. Okay, this one I have done. Okay. So here you have to apply the Gauss law and find the total flux leaving the closed surface. Okay. So the first one you have to do the derivation. Okay. So when you are doing the derivation, so I think I have instructed you how this kind of questions should be done. Okay. Uh, for example, so normally Gauss law, using the Gauss law, we are uh, finding the flux leaving that is perpendicular to the surface. Okay. So you need to verify, you need to get the perpendicular surface. Okay. You need to find the perpendicular surface. Then you need to do the uh, surface integration. That is what you need to do. For example, let's say that if you are going to do the surface integration in uh, uh, X and Z plane, X and Z plane, okay? So dx, dz, okay? So if you are going to do it dx and dz, this plane is definitely perpendicular to y, okay? So the y hat should be there, okay? That means y hat according to this, okay? So we use a y for the unit vector, okay? This is the unit vector, okay? So you need to do this integration, okay? So this d is there, okay? Then you need to find the x limit, sorry, here is the z limit and x limit, okay? So you have to do this integration, okay? For example, if you are going to do this integration, this one, ay hat dot ay hat, uh, you have a value there, okay? So, so that value will be 3x square y square, ay hat, it is 1, okay? So you have to do dx, dz, uh, this z and x, using z and x limit, okay? So, but this part will cancel out because ax dot ay is equal to 0, okay? Because it has 90-degree variation, 90-degree angle, okay? So that is the dot product, okay? So you need to consider the uh, definition of the dot product, that is a dot b is equal to a magnitude into b magnitude cos theta. Theta means the angle between this a and b vector, okay? So this is the dot product of a and b vector, okay? So if cos theta is 90, that means if you consider unit vector in x direction and another unit vector in y direction, okay? So this two has 90 angle, so cos 90 will be 0, okay? So ax into ay will be 0, okay? So this part is cancelled out and you have to do the evaluation only for this part, okay? Likewise, you have to select the uh, proper surface and you need to verify the surface limit, the two variable limits, then you have to do the integration, okay? So that is it. That's it, okay? And as I can remember, I have done another question, I think this one, okay? I have done this one, okay? So here you have to do the uh, div evaluation, divergence. You have to find the divergence. This is the gradient operator, okay? So if you get the gradient operator uh, as a dot product with a vector, okay? So this is called as divergence of this D, okay? So you need to evaluate, you need to be able to evaluate this divergence in the three coordinate system, okay? X, Y, Z, and spherical coordinate and cylindrical coordinate, okay? So these equations are given. So you have to directly use that equation. Okay. So this is the divergence of the in a rectangular coordinate. You need to remember this one. Maybe not no need to remember, but because the exams are open book, okay. But you need to know how to apply this when you need to find the divergence in a given vector in x, y, z coordinate, okay. And this is the divergence in D in cylindrical coordinate and spherical coordinate, okay. So, so this is the basic one. This is the basic one, the standard one, okay. And this sign cylindrical and spherical coordinates, okay. So it has some uh, other parts also, okay. Uh, so as I can remember, um, okay. So as I can remember, uh, we have done, okay. So this first, for this vector, you have to evaluate the divergence in rectangular coordinate, this one in spherical coordinate, and this one is given in cylindrical coordinate, because here we have, sorry, this is spherical coordinate, r theta 5, that is spherical coordinate, okay. And this one is cylindrical coordinate, okay. This one is in cylindrical coordinate, okay. He said rho 5Z, okay, rho 5Z. So that's coordinate sign, uh, cylindrical coordinate. This is spherical coordinate, okay. So this one easily you can evaluate, okay. And as I can remember, we have evaluated this one also, the cylindrical coordinates divergence, okay. So to have idea, we will try to evaluate this one, okay. We will try to evaluate the divergence of this one using the spherical coordinate, okay. So then you need to know that equation, that identity, okay. So this is the identity, okay. So if I write it somewhere, okay, I will write it somewhere here, okay. So if the divergence given in spherical coordinate, okay, div D is equal to 1 over r square daba r square dr, okay. So r square is there, okay. But in cylindrical rectangular coordinate, this coefficients and this part is not there, okay. Plus 1 over r sine theta daba t sine theta d theta, sine theta d theta. So sine theta d theta, okay. Plus 1 over r sine theta, again 1 over r sine theta daba d5 and daba phi. Okay. So this is the identity to the uh, evaluate the divergence in spherical coordinates. Okay. So you are given the questions. Okay. So if I see the question again, yeah, this one. Okay. So D is given. D. Actually, this is D is the uh, charge density. Okay. This C is the surface charge density. It is a surface charge density. Okay. Not the volume charge density. It is a surface charge density. So it is given as 2r sine theta sine phi ar plus r cos theta sine phi theta plus r cos phi a phi. Okay. So this is the D, the the charge density. Okay. So this is Coulomb per square meter. Okay. So this is the surface charge density. Okay. Uh, so you need to evaluate the divergence. Okay. Of this D using this identity. Okay. So this identity is in spherical form. Okay. Spherical coordinate. Okay. So we will see how to apply it. It is not much difficult. Okay. So this dr means the AR component, this one. DT means the AT component, A theta component, this one. D phi means this phi component, this one. Okay. So very easily you can write divergent D, that is equal to 1 over R square is there. Okay. So daba R. Okay. R square is there. Okay. And this one, daba R, dr section, this one. Okay. So that will be 2R sine theta sine phi. Okay. So that is that. Okay. Then plus 1 over R sine theta, 1 over R sine theta. Okay. So daba theta. Okay. So sine theta is here, sine theta. So here you have cos theta sine phi. Cos theta sine phi. Okay. So that is daba theta. Then plus 1 over R sine theta, daba phi. So this is d5, okay? Daba d5. D5 means this one, R cos phi. R cos phi. Okay? So you have to do this evaluation, okay? So that is very easy, okay? So diode divergence of D is equal to, so if you evaluate this one, this is R square 2R. So it will be 2 to the 2 into R to the power 3, okay? So if you if you differentiate it with respect to R, okay, so this term will be 1 over R square is there, okay, this will be, this is 2, no? 2 into 3, so it will be 6, R3 is there, so it will become R square sine theta sine phi. Okay. So when you are differentiate with respect to R, this theta and phi are constant. Okay, so no change like this. Okay, so this is the first one. Plus, so if you consider this one, now now you can see that this R square cancel it. Okay, so it will be 6 sine theta sine phi. Okay, so here R sine theta is there. Okay, and you need to evaluate this one, okay? So here sine theta cos theta, okay? Sine theta cos theta, maybe you can write this as uh, cos 2 theta, sine 2 theta, sine 2 theta divided by 2, no? Okay, because sine 2 theta is equal to sine theta cos theta plus cos theta sine theta. So 2 sine theta cos theta is equal to sine 2 theta. Okay, so sine theta cos theta is equal to sine 2 theta divided by 2. Okay, so if you integrate this one, if you differentiate this one, it will be cos 2 theta theta, cos 2 theta and 2, cos 2 theta 2, no? Okay, or maybe you can evaluate this as a 2, this is a product, no? Okay, so maybe you can differentiate this as a product. Okay, so sine 5 is a constant, you can keep the sine 5 here. Okay, I think r part is there. Okay, the r is also there, this r is there. Okay, so r sine 5 is there. Okay, so you can evaluate this one. You can keep cos theta, evaluate sine theta. So cos theta into sine theta, that is again cos theta. Okay, plus cos theta. You can keep sine theta. Then cos theta, it is minus sine theta. So it will be minus sine theta. Okay. Again, I think this is cos 2 theta. No? This is also cos 2 theta. Okay. This is again cos 2 theta. Okay. So this is equal to cos 2 theta. So I think the answer is correct. Okay. So you will get this one. Okay. So here you can see that then again these are cancelled out, here sine theta, here sine 5, and this part will be cos 2 theta. Okay. Plus this one 1 over r sine theta, 1 over r sine theta, r cos 5. Okay. Then it will be r sine 5 minus. Okay. So this r are cancelled out. So you will have minus sine 5 sine theta. Okay. So that is the divergence. Okay. So check whether if I am doing any mistake. Okay, if I am doing any maybe simplification mistake, don't worry. But this is the procedure. Okay. So r square cancel out, and here you have 6 sine theta sine 5 plus, if you consider this one, this is cos theta cos square theta minus sine square theta, that will be cos 2 theta. So r cancel out. So you will have cos 2 theta sine 5 divided by sine theta. Okay. Plus r cancel out here. This is minus sine 5 divided by sine theta. Sine 5 divided by sine theta. So this is the divergence of D. Okay. Actually, according to the Maxwell law, this divergence is equal to the unit, sorry, the volume charge density at a point. Okay. So that is the Maxwell third equation. Okay. So anyway, this is how the divergence is evaluated. Okay. For that one, you need to know how to apply uh, the spherical coordinate, cylindrical coordinate, and Cartesian coordinate or rectangular coordinate identities to evaluate the divergence. Okay. Okay. So in the class we have done this one also. Okay. And this one also, I think this one, yeah, this one also we have done. This is also not much difficult. Okay. So here you have to find the volume charge density. That means you have to evaluate the divergence of D. Okay. So you can see that this is only Z direction. Z part is there. So XY parts are uh, cancel out. Only Z part is there. So you have to get the DABA, the this one, this AZ part with respect to DABA Z. Okay. So within this limit, you will have, if you differentiate this with respect to Z, rho Z, so you will have rho naught, and 2D, this is a constant and it will be 0. Okay. So the answer will be this one. Okay. So this is the divergence D. Divergence D at this time is equal to rho naught. Okay. So if you consider divergent D for this one, again rho naught minus rho naught is Z, so you will have minus rho naught. If you get the divergence here for this section, divergence D, again you will have minus rho naught. Okay. So that is the answer. Okay. So for others, D is 0. That means the divergence also will be 0. Okay. So the divergence delta D will be rho naught for this uh, region minus 2D Z minus C minus rho naught, that is 0 to Z 2D. Okay. So this is the answer. Elsewhere 0. Okay. Find the volume charge density as a function of position everywhere. Okay. So actually we have found the volume charge density. Okay. So this is D is coulomb per meter. Here we have found coulomb per uh, 3 to the power meter. Here coulomb per square meter. This is meter 3. Okay. This is also coulomb per M3. Okay. Because this is a volume charge. We have found the volume charge here. Okay. So that is the Maxwell equation. This is the Maxwell equation. Okay. Okay. Then determine the electric sparks that pass in the surface. Okay. So here you have to do, again, you have to do the surface integration. Okay. Surface integration. So that is not much difficult. Okay. So you can see that this is only in a Z direction. Okay. This D is in a Z direction. Okay. This direction, a Z direction. Okay. So this a Z direction is only perpendicular to XY plane. A Z direction is only perpendicular to XY plane. Okay. So you have to evaluate the surface integration in XY plane. Okay. That means dx, dy. Okay. So by default, you will have AZ. Okay. So AZ is multiplied by this one. You will have only rho naught Z plus 2D. Then you have to evaluate dx, dy. Okay. So the appropriate x and y limits are there. Okay. So x limit is this one, y limit is this one. Okay. So you need to do the y limits from b minus b to plus b, x limits minus a to plus a. So you have to evaluate this one. Okay. You have to evaluate this one. Then you will have the total electric flux that is passed in this direction. Okay, XY plane in this direction. So if you need to find at Z is 0, so here once you complete the integration, you can apply Z is equal to 0. Then you can calculate this one. Okay, calculate this one. The total charge passing through XY plane in this direction. Okay, and for the other direction, you need to consider this one. It will be minus and it will be minus direction. So again, minus, minus, it will be plus. So same evaluation you have to do, but this will be minus, okay? But at this time, this will be minus, okay? This time, this will be minus, because here, this for this region is at minus 2b, okay? So this will be minus, so you have to do this surface integration, okay? The same limits are there, minus x from minus a to plus a, y from minus b to plus b. Then you can calculate the total flux that is passing through the xy plane in this direction. Minus is z direction, this is plus is z direction, okay? And that value also will be a plus value. Then to find the total flux, you have to add them together, okay? So I think as I can remember, we have done one or two example like this, okay? So I'm not going to do it, okay? Just try to do it, okay? So as I can remember, those are the uh, questions we have done in that physical session, 3.17, 3.21, and 3.24, okay? So try to do these questions by yourself, okay? If you have any problem, maybe you can contact that some students attended to that physical class, okay? So you can get the instruction from them. So if you have any problem, you can ask me also, okay? Then I can help you, okay? So we will do another question, try to do another question, okay? So we will do this one, 3.25 example, okay? So already I have write it here, okay? So I'm not, so, so we will do this one, okay? So, it is stated that the spherical shell is there. So that is definitely spherical coordinate. Okay. Okay. Spherical coordinate. Okay. So always keep remember that spherical and cylindrical coordinates are what is called. They are not unique. Okay. Because this x, sorry, this is z, y, x direction, these directions are fixed, okay? These direction are fixed. You have to use your right hand rule or left hand rule to get these directions, okay? So these directions are not depend on the points, okay? But if you consider any point, okay, in spherical coordinate, okay? So this r direction, the direction of this r is dependent on this point. No? If you select another point, so the r direction will be changed. Okay. So this in spherical coordinates and cylindrical coordinates, the directions are relative. Directions are relative, sapeksha. Right? But x, y, z, those directions are unique. Okay. So those are already predefined directions, x, y, z, but spherical and uh, cylindrical coordinates, those are not uh, those are not uh, fixed. Okay, those are relative. Okay. Um, okay, then I will try to do this one. Okay, so you can see that within the spherical shell, okay, the R is between 3 and 4. Okay, so here um, one R is 3. Okay, another R is okay. So this is the spherical shell. This is the spherical shell. Okay, this is the spherical shell. Okay. the electric flux density is given as this one. Okay. So the electric flux density is given like this. Okay. In this D. Okay. So this is the surface electric flux density. Okay. Then you need to find the volume charge density. Okay. So volume charge density at R is equal to 4. Okay. So you know that if you can, so you have to use the Maxwell third equation. Okay. So divergence of D is equal to rho V. Okay. So this is the Maxwell third equation. So you have to apply this one. So what you have to do, you have to simply find the divergence of this one. Okay. Divergence of this D. Okay. So you have to use the spherical coordinate divergence. Okay. This one. Okay. So you can see that we have only a r. So r direction vector is only there. No theta and phi direction vectors are there. Okay. So this theta and phi, these terms will be 0. We have to consider only this term. Okay. So that is, if you consider divergence of D, in this case, 1 over r square, dabba r square. So this is the dr. Okay, this is the dr component, that is 5r minus 3 to the power 3. Okay, so plus the 5 components part will be 0 and this also will be 0 because there is no any a theta and a phi components. Okay, so you have to only evaluate this derivation. Okay, so that is not much difficult. Okay, so very easily we can do it. Okay, so maybe one way is you can expand this and you can multiply this one and you can evaluate. Okay, so I will do it I don't know, I can't remember the expansion of this term. Okay, so I will do it as a multiplication. Okay, so 1 over r square is there. Okay, so what you have to do, you can keep this one r square, then you can evaluate this one, that is 5r minus 3 to the power 3. So 3 will come up. So 15 r minus 3 square. Okay, 3 minus 1 plus you can keep this one 5 r minus 3 to the power 3. Then you will have again this one, that is 2 r. Okay, so you have this one. Okay, so you can further simplify this divergent D. Okay, so it will be so you can see that so you can get 1 r here. Okay, 1 r here and 15 r minus 3 is square here. Okay, so r square is there. Okay, and here you will have r plus the r you get. So you can get 50. Okay, you can get 5. Okay, so 3 is here. 3r. I think my simplification is correct. Okay, I get so I get out the common factor r into 5r minus 3 square. Okay, and I will have 3 r 3r because 1 r I have get out, this one r. Okay, 3R. Then here I get 5R minus 3. Okay, so 1R minus 3 is there. Okay, R minus 3 is there, and 2R. 2R means 2R square, 6R. Okay, so this kind of result you will get. Okay, so maybe just try to evaluate this. Okay, um, maybe I have done some what is called simplification error. I think no error, no. R square is there. Okay, R square is there. So I will get R. So R will be there. So 5R minus 3 square. So 5, 3 will be there plus. So 5R minus 3 already takes. So 1R minus 3 is there. May how the may Gunawardana may ඔකට මිඩ් එක තියෙනවද?
සර් මොකක්ද මොඩියුල් එක දන්නේ නැහැ.
Electromagnetism. ඔයා දැන් මේ electromagnetism එක නේද join උනේ?
ඔව් සර් මම ඒකට තමා මේ
ඔව් ඒකේ අද මේ මිඩ් එක දාලා තිබ්බා. ඔයාට ආවේ නැද්ද මැසේජ් එක? ඒකේ LMS එක දාලා තිබ්බා උදේ සර්.
ඒක මට නම් ආවේ නැහැ සර්.
කමන්නේ ඔයා දැන් log වෙන්න LMS එකට. දැන් 6ට පටන් ගන්නනේ.
හරි සර් ඕකේ.
හරි 6ට පටන් ගන්න මේ ටක් ගාලා log වෙලා ඒක කරලා අප්ලෝඩ් කරන්න මම මේ කරන මේවා ටික මම ඔකටට දාන්නම්. හරි
හරි සර් ඕකේ.
බලන්න මේ LMS එකේ තියෙනවද බලන්න. මොකද ප්‍රශ්නයක් තිබ්බම මට කියන්නකෝ. හරි
හරි ඕකේ.
ඔයාගේ ඉන්න අනිත් කට්ටියටත් කියන්න. පැටර්ලෙන්ට අනිත් කට්ටිය ඉන්නවනම් කියන්න මේ මිඩ් එක කරන්න කියලා.
හරි ඕකේ සර්.
හරි.
thank you.
Okay, I think this simplification is correct. Okay, so finally, du. So this is I will write like this. Okay, du d is equal to r. This one cancel out. So we will have 5r minus 3 square divided by r. Okay. And here we have 3r, 2r square minus 3r. Okay, so we will have 2r square minus no, this is 6 no? Yeah, 6r. Okay, so we will have minus 3r here, 2r square. You can get again r out. This r cancel out. Okay, so we will have 2r minus 3. Okay, so this is the divergent 3. Okay, check this. Okay, I think the simplification is correct. Okay, so again I get 1r here, then there is another r, no? That r cancel out. Okay. This, so we have r here, no? So I can cut 1r here also. Okay, so 6 minus 6 plus 3, it will be minus 3 and plus 2r. Okay, so this is the divergence. Okay, so you have to evaluate the volume charge density at r is equal to 4. Okay, so this is volume charge density. Okay, so this will be Coulomb per meter power 3 meter. Okay, not Coulomb per square meter. Okay, so you will have this one. Okay, so if you want to find the V at R is equal to 2, R is equal to 4, so you can apply R is equal to 4 here. Okay, so you can apply 4 here. Then you will get the V at 4 R is equal to 4. Okay, so substitute R value here. Then you can find the charge density. Okay. Then what is the electric flux density at R is equal to 4? Okay. So here we have used Maxwell. Okay. So what is the electric flux density at R is equal to 4? Here, I think we have to use the Gauss law for the B, part B. Okay. I will write it here. Okay. So D is equal to 5 R minus 3 to the power 3. 5 R minus 3 to the power 3 AR. Okay. So this is volume charge density. Okay. So this is like this if you have this pair. Okay. So this volume charge is the volume charge is inside this some kind of cell. Okay. Then if you ask to find the volume charge, flux density, if you ask to find the flux density, this is the flux density now. Okay, so this is the flux density. Actually here, for this one, you no need to apply the Gaussian law, no? Because this is flux density. This is flux density. This D is the flux density, no? This D is the flux density, no? So if you want to find the flux density at R is equal to 4, so you can simply apply 4 here. Okay. So 4 minus 3, it will be 1 to the power 3. So actually this, for the B, you will have flux density 5, no? 5 AR. Okay, that is the flux density. Okay, so B, this is the flux density. So you are asked to find the flux density at R is equal to 4. Okay, so here you no need to find the Gaussian law. Okay, so this flux density is given as a function of R. Now you are asking to find the flux density at 4. Okay, so instead of R, I apply 4 here. 4 minus 3, it will be 1 to the power 3. So the answer will be 5 AR Coulomb square meter. Okay, so this is the flux density at R is equal to 4. Okay, that is 5 AR. Okay. Okay, so I think that is the answer. And how much electric flux leave the sphere? Okay, now you are asked to find the electric flux. Okay, so the flux density is given. Flux density is given. This is the flux density. Now you are asked to calculate the total flux. So that one you need to calculate. You need to apply the Gaussian law. In Gaussian law, what is it stated? In Gaussian law, okay, the total flux through a surface, okay, through a surface that is perpendicular, the perpendicular to the surface, surface is equal to Q, no? Okay, the total charge, that is the Gauss, that is the Gauss law. Okay, so here you have to find the flux leaving the surface perpendicular. Okay, so that is again a sphere. That is again a sphere. Okay, so the flux density is there. Flux density is given. Okay, flux density is given. That is flux density is 5 r minus 3 to the power 3 ar. Okay, this is the flux density, surface flux density. Okay, so you are asking to find the total flux through the surface. Okay, this is the flux density. Then you have to find the surface. Okay, you have to find the total flux through the surface. Okay, so that means you have to do the surface integration. Okay, so the surface will be d theta and d phi, in d theta and d phi. Okay, so so the flux will be perpendicular to this surface. So AR is there. Okay, so uh, so the theta, sorry, the phi is from 0 to 2 phi, and theta is from 0 to 5/2, no? 0 to 5. Theta 0 to 5, 0 to 2 phi. Okay, so this is the limits for the d theta and d phi for a total sphere. Okay, so AR dot product you will have 1. So you will have to do this integration. Okay, so simply it will be 5 r minus 3 square, that is a constant. Okay, so if you consider theta, d theta, so the answer is theta from 0 to 5. So you will have 5 here. Again 5 from 0 to 2 phi. So you will have 2 phi here. So I have integrate this and apply the limits. Okay, so theta from 0 to 5, that is 5. Again 5 from 0 to 2 phi, that is 2 phi. Okay, so I will have 5 r minus 3 square 2 phi square. This is the answer. Okay, actually this is the total flux that is measured in Coulomb. Okay, because total flux is equal to the total uh, total flux is equal to total Q enclosed by the surface. Okay, okay, so the flux and Q is equal, so Q measured in Coulomb, so flux also measured in coulombs. Okay, so this is the answer. So here the R is equal to 4. R is at 4, so you can apply R here. So again, you will have 10 phi square. Okay, so that is the answer. I think that is not much difficult question. No? It's somewhat simple. Okay. How much charge is contained within the sphere? Okay, so again you can use how much charge is contained within the sphere. So the flux, the total flux equal to the total charge, no? So flux is 10 phi square. So the charge is also 10 phi square. Okay. So I think that is that. Okay. So I think that question is not much difficult. Okay. So I will do another question also.